Oftentimes we have systems where there are two parallel forces that are being imposed on our system. And when that happens, we call that a force couple system. Some people call it a force dash couple system. Some people will call it just a couple system. There's all kinds of different names. What they're really trying to say, and here's a physical example where this might happen, is when we put two equal opposite forces on them, the translational effects of these two are going to be zero, right? You got F going in one direction and a force going the exact opposite. They're going to cancel each other out, except for when they're separated out by this distance, this perpendicular distance. Then, in that case, there's going to be a rotational effect, and so you get a pure moment that is purely this perpendicular distance times this force. This is how external moments get applied to a system. Now, one other little small piece here. These two forces on this cruciform tire arm that are going equal opposite in direction are going to create no translational effect on the tire iron, but what they're going to do is ultimately there's going to be a bending effect in this one piece that happens as they're doing this push-pull business, but on this other shaft, that's where you get torque. So a torque is really a subset of moments. It's a special class of things. We're going to just focus here on the systems that have just two parallel forces and a specific distance in between. So take this little block that we have down here below. We've got then a 20-pound force coming out at us and a 20-pound force going back in, and they're both parallel to the z-axis. Indeed, one of them is right on the z-axis. So this moment that is caused by this is equal to 20 pounds times 6 inches, or 120 pound-inches. Now, I'm not going to worry too much about the direction here because that gets into a couple of other aspects of things, but one simple way to do this is to use the double-headed arrow approach. And so let me really draw that out a little bit bigger because it kind of disappears. It's a little bit better. Take the right hand, thumb going along the direction of the arrows, and the fingers then would show you the tendency of rotation. And so that I like doing it that way. Alright, now you got this other one. Note you got 30 pounds times 4 inches. The forces are in two different directions here. One going to the positive x-axis, one going the negative x-axis, and there again we're going to get 30 pounds times 4 inches, or 120 pound-inches, and it's also going to cause rotation in the same direction as before. So these two systems are statically equivalent, right? They're going to have zero translational effect, but they're going to have a rotational effect. Doesn't mean that deformations are the same, but we're ignoring that in this field of study. We're only looking at the static equivalency here. And then finally you get the same thing up here. These are up in the upper corners of the box, still along the positive and negative x-axis, separated by 4 inches, and so that will also be 120 pound-inches. And what we ended up with then was three statically equivalent systems. In this case, no force translation is a net effect. It looks like we're imposing them all in the same one, but this is by doing a different color for M, we're trying to suggest that that's a statically equivalent. We really should draw each one of these three blocks separately, and they would only have these three moment vectors shown.